Right now, 642 light-years away, a dying star is preparing for one of the most violent events in the universe. Betelgeuse, the massive red supergiant marking Orion's shoulder, could explode at any moment, not in human terms of any moment, in cosmic terms, which means tonight, or in 100,000 years. We cannot predict it precisely, but when it happens, Earth will witness something no human has ever seen, a supernova visible in daylight, bright enough to cast shadows at night. A new star appearing in the sky, outshining everything except the sun and moon. For weeks, perhaps months, Betelgeuse will dominate our view of the cosmos. Then it will fade, leaving behind a glowing remnant where one of the most famous stars used to shine. But here is what nobody tells you about supernovae. They are not just bright, they are transformative. The explosion will send a shockwave through space at 10% the speed of light. It will release more energy in seconds than our sun will produce in its entire 10 billion year lifetime. The blast will forge elements that do not exist anywhere else. And the radiation, the high-energy particles, the cosmic rays, all of it will travel through space toward Earth. The question is not whether we will be affected. The question is how much. Scientists have studied this scenario extensively. They have calculated distances, measured radiation levels, modeled atmospheric effects. The consensus is clear. We are probably safe. Betelgeuse is far enough away that the explosion will not sterilize Earth or strip our atmosphere. But probably safe is not the same as certainly safe. There are uncertainties, variables we cannot fully predict, edge cases where things go wrong. And understanding those possibilities requires understanding what happens when a star, 20 times the mass of the Sun, tears itself apart in nuclear fire. If you want to know what humanity would actually experience if Betelgeuse exploded tonight, not the simplified version, not the reassuring platitudes, but the real physics and real consequences, then stay with me. We are about to explore one of the most spectacular and potentially dangerous events the universe can produce, and it is happening closer than you think. The star that cannot decide if it is dying. Betelgeuse has been behaving strangely. In late 2019, it began to dim. By February 2020, it had lost more than 60% of its normal brightness. Astronomers watched with instruments ranging from backyard telescopes to space-based observatories. The dimming was unprecedented in recorded history. Speculation erupted. Was this the precursor to supernova? Were we witnessing the final days of a star that has shone for millions of years? The dimming event triggered intense scientific investigation. Researchers used every available tool to understand what was happening. The Hubble Space Telescope captured ultraviolet images. Ground-based infrared telescopes measured temperature variations across the star's surface. Radio telescopes tracked changes in the surrounding gas. The data revealed something unexpected. Betelgeuse had not suddenly entered its death throes. Instead, it had ejected a massive cloud of gas and dust that temporarily blocked our view of the star's surface. This is called a surface mass ejection, and it is common in red supergiants. These stars are so massive and so luminous that radiation pressure pushes material off their surfaces continuously. Betelgeuse loses mass equivalent to Earth's mass every year. This ejected material forms a circumstellar envelope, a shell of gas and dust surrounding the star. When particularly large ejections occur, they can create temporary dimming as the material passes between us and the star. The 2020 dimming event was one such large ejection. Computer models reconstructed what happened. A convective cell, a massive bubble of hot plasma, rose from deep within Betelgeuse's interior to its surface. When it reached the photosphere, the visible surface layer, it cooled and released a pulse of gas. This gas expanded outward, cooled further, and condensed into dust grains. The dust cloud then drifted between Betelgeuse and Earth, blocking a significant fraction of the star's light. By mid-2020, the cloud had dispersed enough that Betelgeuse returned to normal brightness. But the dimming event revealed something important. Betelgeuse is unstable. Its massive size and intense radiation create conditions where the star cannot maintain equilibrium. The outer layers expand and contract over timescales of months to years. Convection cells larger than the entire orbit of Mars rise and fall within the star. Material is constantly being ejected. This instability is a symptom of late-stage stellar evolution. Betelgeuse is in the final phase of its life, burning through its remaining nuclear fuel at an accelerating rate. Red supergiants like Betelgeuse form from stars that began their lives with 10 to 40 times the Sun's mass. These massive stars burn through hydrogen fuel quickly, in just a few million years compared to the Sun's 10 billion. When core hydrogen is exhausted, the core contracts and heats up. This ignites hydrogen in a shell around the core. The energy release causes the outer layers to expand dramatically. The star swells to enormous size. Betelgeuse is roughly 900 times the diameter of the Sunday. If placed at the center of our solar system, it would extend past the orbit of Jupiter. Inside the core, nuclear fusion continues, but in different forms. After exhausting hydrogen, the core temperature rises high enough to fuse helium into carbon and oxygen. This phase lasts about 1 million years for a star of Betelgeuse's mass. Then carbon fuses into neon and magnesium. Neon fuses into oxygen. Oxygen fuses into silicon. Each stage burns faster and produces less energy than the previous one. Silicon burning, the final stage, lasts only a few days. The core becomes a layered structure, with iron in the center, surrounded by shells of silicon, oxygen, neon, carbon, helium, and hydrogen. Iron is the end of the line. Fusing iron requires energy rather than releasing it. When the iron core reaches about 1.4 solar masses, electron degeneracy pressure can no longer support it against gravity. The core collapses. In less than a second, material falling inward at 1/4 the speed of light compresses to nuclear density. The collapse halts abruptly when the core becomes a neutron star. The infalling material rebounds off this incompressible surface, creating a shockwave that propagates outward through the star. This shockwave tears the star apart. This is a core collapse supernova. Betelgeuse is currently somewhere in the later stages of this process. It has exhausted core hydrogen and helium. It may be burning carbon or even heavier elements. The exact stage is unknown because we cannot observe the core directly. But the star's behavior, its size, luminosity, and surface activity all indicate it is approaching the end. The iron core is building. When it reaches critical mass, collapse will occur. The timescale is uncertain. It could happen tomorrow. It could happen in 100,000 years. Stellar evolution models cannot predict this precisely. The uncertainty stems from incomplete understanding of mass loss rates, convection, and rotation. These factors affect how quickly the star burns fuel and how much mass remains in the core. A star that loses mass slowly will reach core collapse sooner because it retains more mass in the core. A star that loses mass rapidly may never form an iron core large enough to collapse. The balance is delicate and depends on variables that are difficult to measure. Recent studies have attempted to narrow the timeline. One approach uses asteroseismology, the study of stellar oscillations. Betelgeuse's surface pulsates with multiple frequencies. These oscillations are caused by sound waves trapped inside the star. By analyzing the frequencies, researchers can infer internal structure. The data suggests Betelgeuse is currently burning carbon in its core, which places it roughly 100,000 years before the supernova. But uncertainties in the models mean this estimate could be off by an order of magnitude. The truth is, we do not know. Betelgeuse could explode tonight while you read this, or it might already have exploded and the light is travelling toward us, set to arrive in 642 years. Or it will continue shining for millennia, outlasting human civilization. This uncertainty is frustrating but fundamental. Stars this massive are rare, and their late-stage evolution is poorly understood because observational data is limited. Betelgeuse is one of the best-studied red supergiants, yet it still keeps its secrets. What we can say with confidence is that when Betelgeuse does explode, it will be the astronomical event of human history. No supernova has been observed this close since 1604, when Kepler's supernova appeared in the constellation Ophiuchus at an estimated distance of 20,000 light-years. Betelgeuse is 30 times closer. The explosion will be far brighter and far more spectacular than anything recorded in modern times. And despite the distance, it will have measurable effects on Earth. Understanding those effects requires understanding what happens during a core collapse supernova, the collapse that powers the universe. The core of a massive star spends millions of years building toward a single moment. Fusion reactions create progressively heavier elements, each stage burning hotter and faster than the last. Hydrogen fuses into helium over millions of years. Helium fuses into carbon and oxygen over 1,000,000 years. Carbon burns for thousands of years, neon for a few years, oxygen for months. Silicon burns for days. Then the core is iron and fusion stops. Iron 5,6 is the most stable nucleus. It has the highest binding energy per nucleon of any element. Fusing lighter elements into iron releases energy. Fusing iron into heavier elements requires energy input. When the core fills with iron, the star faces a thermodynamic dead end. No more energy can be extracted through fusion. The radiation pressure that supported the core against gravity disappears. The only thing holding the core up is electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle. When the iron core reaches 1.4 solar masses, the Chandrasekhar limit, electron degeneracy pressure cannot counteract gravitational collapse. The core implodes. Material falls inward at speeds reaching 70,000 kilometers per second, 1/4 the speed of light. In less than a second, the core shrinks from the size of Earth to the size of a city. Densities reach that of atomic nuclei. Protons and electrons are squeezed so close that they merge, forming neutrons and releasing neutrinos. This is neutronization. The collapse halts when the core reaches neutron degeneracy pressure, the same quantum effect that creates electron degeneracy, but applied to neutrons. The core rebounds. The abrupt halt sends a shockwave propagating outward through the infalling material. This shockwave is the supernova. It carries enormous energy, around 1044 joules, equivalent to the Sun's total energy output over 10 billion years, released in seconds. The shockwave blasts through the star's outer layers, heating them to billions of degrees. Nuclear reactions ignite throughout the ejected material. Elements heavier than iron are synthesized in seconds. The visible explosion is powered primarily by radioactive decay. The shockwave creates vast quantities of unstable isotopes, particularly nickel 5,6 and cobalt 5,6. These decay with half-lives of days to months, releasing gamma rays that heat the ejected gas. The heated gas expands and glows, creating the bright optical display we observe as a supernova. Peak brightness occurs when the expanding gas becomes optically thin, allowing the radioactively heated interior to shine through. For a star like Betelgeuse, this happens about 2 weeks after core collapse. But most of the energy is carried away by neutrinos. About 99% of the collapse energy escapes as a neutrino burst lasting 10 seconds. These neutrinos carry 1046 joules of energy. A supernova 10 parsecs away would bathe Earth in enough neutrinos to deliver a lethal radiation dose. Fortunately, Betelgeuse is 200 parsecs away. The neutrino flux at Earth will be detectable but harmless. Neutrino observatories around the world will record the burst hours before the optical light arrives, providing the first warning that Betelgeuse has exploded. The mechanics of core collapse are well understood theoretically but difficult to observe. The process happens deep inside massive stars, where direct observation is impossible. Our understanding comes from computer simulations and observations of other supernovae. Supernova 1987A, which exploded in the Large Magellanic Cloud in 1987, provided crucial data. Neutrino detectors on Earth recorded a burst of neutrinos 3 hours before the optical brightening, confirming that core collapse preceded the visible explosion. This was the first direct detection of supernova neutrinos and validated theoretical models. The resolution came from more accurate neutrino transport, neutrinos escaping the core deposit energy in the region just outside it. This energy revives the stalled shockwave, driving it outward. The process is called neutrino-driven convection, and it takes roughly a second to develop. Modern simulations incorporating detailed neutrino physics successfully produce explosions, though the exact mechanism remains debated. Rotation, magnetic fields, and instabilities also play roles. Core collapse supernovae are among the most complex events in astrophysics. Betelgeuse's core collapse will follow this same process. When the iron core reaches critical mass, it will implode in less than a second. A neutron star will form, neutrinos will stream outward. A shockwave will tear through the star's envelope. The outer layers, containing hydrogen, helium, and heavier elements synthesized over millions of years, will be ejected into space at 10,000 to 30,000 kilometers per second. This ejected material is the supernova remnant. It will expand for thousands of years, eventually dispersing into the interstellar medium. The explosion will release elements created inside the star: carbon, oxygen, silicon, sulfur, iron, and many others. These elements were forged in the core through fusion. But elements heavier than iron, such as gold, platinum, and uranium, are created during the explosion itself. The intense neutron flux during core collapse allows rapid neutron capture, the R process. Atomic nuclei absorb multiple neutrons before decaying, climbing the periodic table. This process lasts seconds, but produces most of the universe's heavy elements. Every atom of gold in your jewelry, every atom of platinum in your electronics, every atom of uranium in Earth's core was created in a supernova. Stars are the universe's factories, assembling heavy elements from hydrogen and helium. Supernovae are the distributors, spreading those elements into space where they can form new stars, planets, and eventually life. Without supernovae, the universe would contain only hydrogen and helium. No rocky planets, no water, no organic molecules, no life. Betelgeuse's explosion will inject a solar mass of heavy elements into the interstellar medium. This will enrich the local environment, raising the metallicity of nearby gas clouds. Future stars forming in that region will have higher metal content than previous generations. This process has been operating since the first massive stars exploded 13 billion years ago. Each generation of stars incrementally enriches the universe with heavy elements. Our solar system formed from material enriched by countless previous supernovae. We are, quite literally, made of stardust. The energy released from Betelgeuse's supernova will also affect surrounding space. The shockwave will sweep up interstellar gas, compressing it into dense shells. These shells may trigger the formation of new stars through gravitational collapse. Observations of supernova remnants show young star clusters forming at their edges. The death of one star seeds the birth of others. This cycle of stellar life and death drives galactic evolution. Without supernovae, galaxies would be static collections of long-lived stars. With them, galaxies are dynamic, self-recycling systems. But for Earth, the immediate concern is not nucleosynthesis or galactic evolution. It is radiation. The explosion will produce a burst of high-energy photons, gamma rays, X-rays, and ultraviolet light. These will travel toward Earth at light speed. Behind them will come the neutrinos, traveling slightly slower due to their tiny mass. Then the supernova remnant, expanding at a fraction of light speed. And finally, cosmic rays, high-energy particles, accelerated by the shockwave. Each form of radiation poses different risks. When Betelgeuse's light reaches Earth, the first indication that Betelgeuse has exploded will come from neutrino detectors. Neutrinos travel at nearly light speed and interact so weakly with matter that they pass through Earth unimpeded. About 10 seconds after core collapse, a burst of roughly 1058 neutrinos will stream outward from the collapsing core. At Earth's distance, neutrino observatories will detect dozens to hundreds of events. This is far above background rates, and unmistakable. The neutrino burst will arrive hours before the optical light. This delay occurs because optical photons must diffuse through the star's outer layers. The photosphere, where photons can finally escape, is at the star's surface. Material between the shockwave and the surface absorbs and re-emits photons many times. This random walk process delays their escape. Meanwhile, neutrinos pass through the star almost unimpeded. They escape within seconds of core collapse. For Earth-based observers, the neutrino detection will serve as a warning. Astronomers will immediately point telescopes at Betelgeuse. Within a few hours, the star will begin to brighten. The rise is gradual at first. Over the course of a day, Betelgeuse will increase from its normal magnitude of plus 0.5 to perhaps -5, comparable to Venus. After 2 weeks, it will reach peak brightness around magnitude -11 or -12, roughly as bright as the half-illuminated moon. The brightness will persist for weeks to months. The light curve, brightness over time, follows a characteristic pattern: a rapid rise to peak over 2 weeks, a slower decline lasting months. The decline rate depends on how much radioactive nickel was produced. Nickel 5-6 decays to cobalt 5-6 with a 6-day half-life. Cobalt 5-6 decays to iron 5-6 with a 77-day half-life. Gamma rays from these decays power the visible emission. As the isotopes decay, brightness fades. After 100 days, the supernova will have dimmed to magnitude -3, still one of the brightest objects in the night sky. After a year, magnitude +1, comparable to normal bright stars. After 5 years, magnitude +6, visible only through binoculars. This energy will heat Earth's upper atmosphere. Temperature increases of 10 to 50 Kelvin are predicted at altitudes above 100 kilometers. This heating causes the atmosphere to expand. The increased atmospheric density at higher altitudes affects satellites. Orbital drag increases. Satellites lose altitude faster than usual. This is manageable, but requires corrective thruster burns. GPS satellites, weather satellites, and the International Space Station will all be affected. Betelgeuse's supernova will produce a UV flux roughly 10,000 times normal background for a few weeks. This will enhance ozone production temporarily. The ozone layer will thicken. This might seem beneficial, but excess ozone can have negative effects. It absorbs more UV, but also infrared radiation. The stratosphere warms. Atmospheric circulation patterns shift. Weather could be affected, though the duration is too short for long-term climate impacts. The UV radiation will also affect organisms directly. DNA absorbs UV wavelengths around 260 nanometers. This causes thymine dimers, a type of DNA damage. Cells have repair mechanisms, but excessive damage overwhelms them. Skin cancer risk increases. Eye damage from UV exposure causes cataracts. Plants can be harmed, reducing photosynthesis. Marine phytoplankton, the base of the ocean food chain, are particularly vulnerable. A severe UV increase could disrupt ecosystems. However, Earth's atmosphere will shield most surface life. Even at UV wavelengths, the atmosphere absorbs the majority of the flux. Ground-level UV increase will be modest, perhaps 20 to 50% above normal, for a few weeks. This is comparable to moving from a temperate zone to the tropics. Noticeable, but not catastrophic. Humans would need to take precautions. Sunscreen, protective clothing, limit midday sun exposure. But mass extinctions are unlikely. The real concern is not immediate radiation, but secondary effects. The atmospheric heating and ionization will alter chemistry in the upper atmosphere. Nitrogen oxides will form in large quantities. These compounds are catalysts for ozone destruction. After the initial UV burst ends and ozone production returns to normal, the accumulated nitrogen oxides will begin destroying ozone faster than it regenerates. Ozone depletion could persist for years after the supernova fades. Ozone depletion was a major concern in the 20th century due to chlorofluorocarbons. International agreements banned CFCs, and the ozone layer is now recovering. But a supernova could reverse that progress temporarily. Models predict a 20 to 40% ozone depletion lasting several years. This would double or triple surface UV levels. The effects on ecosystems would be significant but not extinction level. Vulnerable species might decline. Agriculture would be affected. Human health impacts would rise. Cosmic rays are another consideration. Supernovae accelerate particles to relativistic energies. Protons, electrons, and heavier nuclei are accelerated by the shockwave through a process called diffusive shock acceleration. These particles, called cosmic rays, travel through the galaxy at nearly light speed. Some eventually reach Earth. Betelgeuse's supernova will produce a burst of cosmic rays that will arrive years to decades after the optical explosion, depending on the path they take through the galaxy's magnetic fields. Cosmic rays pose risks to electronics and astronauts. They can flip bits in computer memory, causing errors. They damage DNA, increasing cancer risk. Earth's magnetic field deflects most cosmic rays, but some penetrate to the surface. The cosmic ray flux from Betelgeuse will be elevated above the background for centuries. However, the increase will be modest, perhaps 10 to 50%. This is detectable, but not dangerous for surface life. Astronauts on long-duration missions or on the Moon will face higher risks and need enhanced shielding. The scientific community will mobilize. Every major telescope on Earth and in space will observe Betelgeuse continuously. Spectroscopy will reveal the composition of the ejected material. Photometry will track the brightness evolution. Neutrino detectors will analyze the burst for information about the collapse. Radio telescopes will monitor the expanding shockwave. The data will refine our understanding of core collapse supernovae and massive star evolution. Betelgeuse's explosion will be the most thoroughly studied supernova in history. The shockwave in space. The visible light and high-energy radiation from Betelgeuse will arrive first, travelling at the speed of light. But behind them comes something slower and more enduring, the supernova remnant itself. The shockwave ejecting material from the star expands at 10,000 to 30,000 kilometers per second, fast by terrestrial standards, but only 1 to 10% of light speed. This material will take thousands of years to cross the distance between Betelgeuse and Earth. When it arrives, it will interact with our solar system in measurable ways. Betelgeuse is moving through space at roughly 30 kilometers per second relative to nearby stars. This motion creates a bow shock, where its stellar wind collides with the interstellar medium. The bow shock is visible in infrared images as an arc of glowing gas ahead of the star. When Betelgeuse explodes, the supernova remnant will replace this bow shock with a much more energetic shockwave. The remnant will expand outward in all directions, but its interaction with the pre-existing circumstellar material will create complex structures. But the remnant expands into a region already altered by Betelgeuse's stellar wind. Red supergiants lose mass at prodigious rates, 10, -6 to 10, -4 solar masses per year. Over millions of years, this creates a bubble of hot, low-density gas surrounding the star. The supernova shockwave will initially expand through this bubble at maximum speed. When it reaches the bubble's edge, where wind-blown material meets undisturbed interstellar medium, it will slow abruptly. This deceleration dissipates energy, brightening the remnant at optical and radio wavelengths. Another consequence is the influx of heavy elements. The supernova will inject a solar mass of newly synthesized elements into the interstellar medium. These elements will mix with existing gas over millions of years. A tiny fraction will eventually reach the solar system. Earth will pass through regions enriched with supernova ejecta. These elements will settle into the atmosphere and onto the surface. Isotopes like Iron 60 and Plutonium 244, which are only produced in supernovae, will appear in Earth's geological record. Scientists have found evidence of past supernovae in ocean sediments. Iron 60 has a half-life of 2.6 million years. It does not occur naturally on Earth. Any Iron 60 found in sediments must have come from space. Cores taken from the Pacific Ocean floor show Iron 60 peaks corresponding to times when nearby supernovae occurred. The most recent peak is about 2 to 3 million years ago, suggesting a supernova exploded within 100 parsecs during that time. Betelgeuse's supernova will add to this record. In 700,000 years, Iron 60 from the remnant will begin raining onto Earth. The quantity will be minuscule, a few atoms per square centimetre per year, but it will be detectable in future ice cores and ocean sediments. Far future geologists, if they exist, will find evidence of this event in Earth's strata. They might correlate it with climate shifts or biological changes. The supernova will leave its mark on Earth's history, a tangible reminder of the connection between our planet and stellar evolution. Geomagnetic storms disrupt the magnetosphere, causing auroras and affecting electrical systems. Satellites experience increased drag and potential damage. Power grids can be affected by induced currents. communication systems face interference. A sustained increase in geomagnetic activity from the approaching supernova remnant could last for thousands of years as the material flows past the solar system. Human civilization, if it still exists in recognizable form, would need to adapt infrastructure to handle the enhanced space weather. The radiation environment in the solar system will change. Cosmic rays accelerated by the supernova shockwave will arrive continuously over millions of years. The flux will peak when the shockwave reaches Earth, then decline as the remnant disperses. During the peak, cosmic ray intensities could be 10 to 100 times higher than present background levels. This would affect any unshielded spacecraft or habitats on airless bodies like the Moon or Mars. For Earth's surface, the atmosphere provides protection. Even a 100-fold increase in cosmic rays would result in only a modest increase in surface radiation levels. Background radiation at sea level is about 0, 1 microsieverts per hour from cosmic rays. A 100-fold increase would raise this to 10 microsieverts per hour, comparable to the dose rate at high altitudes or in high background regions like parts of Iran and India. Noticeable but not immediately dangerous. However, the effects accumulate over time. Cancer rates might increase slightly. Mutation rates in plants and animals could rise. The most significant biological impact would likely be on the ozone layer, not from cosmic rays directly, but from the secondary particles they produce. Cosmic rays entering the atmosphere create cascades of particles, including muons, neutrons, and pions. These interact with atmospheric molecules, producing nitrogen oxides. As mentioned earlier, nitrogen oxides catalyze ozone destruction. A sustained increase in cosmic ray flux would mean sustained ozone depletion. This could last for tens of thousands of years, far longer than the initial UV burst from the supernova itself. One speculative possibility is that the supernova could affect the solar system's trajectory through the galaxy. The shockwave carries momentum. When it strikes the heliosphere, it transfers some of that momentum to the solar system. The effect is tiny, changing the sun's velocity by perhaps a few meters per second over thousands of years. This is negligible compared to the sun's orbital speed of 220 kilometers per second around the galactic center. But over millions of years, small changes accumulate. The solar system's path through the galaxy could be slightly altered, affecting when and where it encounters other supernovae or molecular clouds in the future. The supernova remnant will eventually disperse completely, becoming indistinguishable from the general interstellar medium, but its effects will persist. The enriched gas will eventually collapse to form new stars and planets. Some of those planets might develop life. That life will be composed of atoms forged in Betelgeuse's core and scattered by its explosion. In this way, Betelgeuse's death will contribute to the birth of future worlds, continuing the cycle that has operated since the first stars exploded billions of years ago. For humanity, the arrival of the shockwave is so far in the future that it is nearly irrelevant. 600,000 years is longer than Homo sapiens has existed. Civilization is only a few thousand years old. Predicting what Earth or humanity will be like in 600,000 years is impossible. We might be extinct. We might have colonized the galaxy. Earth itself might be uninhabitable for unrelated reasons. The shockwave will arrive to find whatever has become of our world indifferent to whether anyone is there to observe it. But the immediate effects, the optical display, the radiation, the scientific data, those will impact the current generation, or at least the very near future. If Betelgeuse explodes tonight, people alive now will witness it. Children born tomorrow might grow up seeing a bright new star in Orion. The event will be seared into collective memory, referenced in art, literature, and science for centuries. Even if the physical effects are manageable, the psychological and cultural impact will be profound. The neutron star left behind, when the dust settles, literally, Betelgeuse's core will remain. Compressed to a sphere roughly 20 kilometers in diameter, the neutron star will spin rapidly, powered by the conservation of angular momentum from the collapsing core. This tiny remnant will contain about 1.4 times the Sun's mass, packed into a volume smaller than a city. Densities will reach 17 kilograms per cubic meter, comparable to an atomic nucleus. A teaspoon of neutron star material would weigh as much as Mount Everest. Neutron stars are among the most extreme objects in the universe. Their properties push physics to its limits. The surface gravity is 200 billion times Earth's. An object falling from 1 meter above the surface would hit at roughly half the speed of light. The magnetic fields are trillions of times stronger than Earth's, intense enough to distort electron orbitals and affect the very structure of atoms. Light passing near a neutron star is bent significantly by gravitational lensing, allowing observers to see more than half the surface simultaneously. The equation of state of neutron star matter remains uncertain. At densities approaching that of atomic nuclei, the behavior of matter is not fully understood. Neutrons are packed so tightly that they may dissolve into a soup of quarks, the fundamental particles that compose protons and neutrons. This quark matter would have exotic properties, potentially including superfluidity and superconductivity. Observations of neutron stars provide the only way to test theories of matter at these extreme densities. Betelgeuse's neutron star will be born spinning rapidly. The collapsing core's rotation speed increases as it shrinks, much like an ice skater pulling in their arms. Initial rotation periods of newborn neutron stars are typically 10 to 100 milliseconds. The rapid rotation, combined with the intense magnetic field, creates a pulsar. Charged particles are accelerated along magnetic field lines, producing beams of radiation that sweep through space like a lighthouse. If Earth lies in the path of one of these beams, we will detect regular pulses of radio waves. If Betelgeuse's neutron star becomes a pulsar visible from Earth, it will be the closest known pulsar. The nearest currently known pulsar, PSRJ 437-4715, is about 510 light-years away. Betelgeuse's remnant at 642 light-years would be nearby by pulsar standards. Its radio emission would be detectable by even modest radio telescopes. Amateur astronomers could monitor it. The scientific community would study it intensely, measuring its period derivative, magnetic field strength, and any glitches or variations. Betelgeuse's pulsar would initially be bright in X-rays. Young pulsars, less than a few thousand years old, are often X-ray sources. The high temperatures and particle acceleration near the surface produce X-ray emission. As the pulsar ages and cools, X-ray brightness fades. After 10,000 years, the pulsar would be primarily a radio source. After 1,000,000 years, it might fade below detectability, depending on its magnetic field and rotation period. Another possibility is that Betelgeuse's core collapse produces a magnetar instead of a normal pulsar. Magnetars are neutron stars with magnetic fields 1,000 times stronger than typical pulsars. The magnetic field strength reaches 14 to 1015 Gauss, the strongest magnetic field in the universe. These fields are so intense that they stress the neutron star's crust, causing starquakes and violent bursts of X-rays and gamma rays. Magnetars are rare, only about 30 are known. They are thought to form when the collapsing core has rapid rotation and strong magnetic fields. conditions that amplify the field through dynamo processes. The resulting neutron star has a magnetic field thousands of times stronger than normal. This field decays over thousands of years, releasing energy that heats the star and powers the observed radiation. Magnetars are the most luminous X-ray sources in the galaxy, despite being only 20 kilometers across. If Betelgeuse produces a magnetar, it would be easily detectable from Earth. The X-ray and gamma-ray bursts would be bright enough to affect our atmosphere, potentially causing the same ozone depletion and atmospheric heating discussed earlier. Magnetar bursts are unpredictable and can be extremely energetic. The 27th of December 2004 burst from SGR 1806-20, a magnetar 50,000 light-years away, briefly overwhelmed satellite detectors and ionized Earth's upper atmosphere. A similar burst from Betelgeuse, 80 times closer, would be proportionally more intense. However, magnetars are rare, and Betelgeuse may not have the required conditions to form one. The star's rotation rate is uncertain. Observations suggest a rotation period of roughly 1 year, much slower than the Sun's 25-day period. Slow rotation generally does not produce magnetars. But if Betelgeuse has a rapidly rotating core hidden beneath its slow-rotating envelope, a magnetar could form. The envelope's rotation does not necessarily reflect the core's rotation. In massive stars, differential rotation is common. Another exotic possibility is that the core collapse produces not a neutron star but a black hole. If the core mass exceeds about 2.5 solar masses, neutron degeneracy pressure cannot support it. The core collapses to infinite density, forming a black hole. Betelgeuse's core mass estimates range from 5 to 10 solar masses, well above this limit. However, much of the core is ejected during the explosion. Only the innermost material remains. Whether the remnant mass exceeds the black hole threshold depends on details of the explosion mechanism. If a black hole forms, there will be no pulsar. The supernova will occur as normal, but the collapsed core will be invisible except through its gravitational effects. If the black hole is part of a binary system, it might accrete matter from a companion star, producing X-rays. But Betelgeuse is not known to have a close companion. A solitary black hole would be nearly undetectable, revealing itself only through gravitational lensing of background stars. Whether Betelgeuse's remnant is a neutron star, pulsar, magnetar, or black hole will be determined by the details of the core collapse. We will know the answer when the explosion occurs. Neutrino observatories will provide the first clues. The neutrino burst's characteristics depend on whether the core bounces neutron star or continues collapsing black hole. Radio telescopes will search for pulsar emission in the weeks and months following the supernova. X-ray telescopes will monitor for the bright emission characteristic of young neutron stars or magnetars. The remnant, whatever form it takes, will remain in Orion for millions of years. It will drift slowly through the galaxy, a testament to the violent death of one of the sky's most recognizable stars. Future astronomers, human or otherwise, will study it as we now study the Crab pulsar or the Vela pulsar, remnants of supernovae that exploded hundreds to thousands of years ago. Betelgeuse's remnant will add to this catalogue of extreme physics laboratories, providing data to test theories and refine our understanding of matter, energy, and the life cycles of stars. The scientific instruments waiting for Betelgeuse. The global scientific community has been preparing for Betelgeuse's explosion, even though the timing is unpredictable. A network of instruments spans the electromagnetic spectrum, ready to capture data from radio to gamma rays. Neutrino detectors are operational. Gravitational wave observatories are listening. When Betelgeuse explodes, This unprecedented array of technology will capture the event in detail no previous supernova has received. Neutrino detection is the first priority. Neutrinos will arrive hours before optical photons, providing the earliest warning. Super Kamiokande in Japan, IceCube at the South Pole, and Camland in Japan are continuously monitoring for neutrino bursts. When detected, these observatories will immediately alert the astronomical community through the Supernova Early Warning System, SNOOS. This will give optical astronomers time to point telescopes at Betelgeuse before the visible brightening begins. Super Kamiokande is the largest and most sensitive neutrino detector optimized for supernova neutrinos. It consists of 50,000 tons of ultra-pure water in a cylindrical tank 1,000 meters underground. The water is monitored by 11,129 photomultiplier tubes that detect the faint flashes of Cherenkov light produced when neutrinos interact with water molecules. For a supernova at Betelgeuse's distance, Super Kamiokande will detect 50 to 100 neutrinos over 10 seconds. The exact number depends on supernova details and neutrino physics. IceCube uses a cubic kilometer of Antarctic ice as a neutrino detector. While primarily designed for high-energy neutrinos from cosmic sources, IceCube also monitors for supernova bursts. It is less sensitive than Super Kamiokande for supernova neutrinos, but provides an independent detection. The combination of multiple detectors increases confidence and allows localization of the source through timing differences. The neutrino data will reveal the core collapse process. The neutrino luminosity, spectrum, and time evolution encode information about the neutron star formation, the equation of state of nuclear matter, and neutrino oscillations. If the neutrino burst shows a sudden cutoff, it might indicate black hole formation. If it extends for tens of seconds with complex structure, it suggests convective instabilities in the proto-neutron star. This single burst will provide data equivalent to decades of laboratory experiments on nuclear physics. Optical telescopes will capture the light curve with unprecedented precision. Automated survey telescopes, like the Zwicky Transient Facility, ZTF, and the upcoming Vera-C, Rubin Observatory scan the sky nightly, detecting transient events. When Betelgeuse brightens, these surveys will immediately flag it. Follow-up observations from major observatories will begin within hours. The James Webb Space Telescope, launched in 2021, will observe in infrared. Infrared is crucial for studying the dust that forms in the cooling ejector. Within weeks of the explosion, silicate and carbon dust grains will condense, absorbing optical light and re-emitting it in infrared. JWST will track this process, measuring dust masses, compositions, and temperatures. The data will test models of dust formation, important for understanding how supernovae seed the interstellar medium with the raw material for planets. Ground-based optical telescopes will provide continuous monitoring. Large telescopes, like the European Southern Observatory's Very Large Telescope, VLT, in Chile, and the Keck Observatory in Hawaii, will obtain high-resolution spectra. Spectroscopy reveals the chemical composition of the ejected material, the velocities of different layers, and the temperature and density structure. Time series spectroscopy will show how these properties evolve, constraining models of the explosion mechanism. Radio telescopes will detect synchrotron emission from the shockwave. As the shockwave expands, it accelerates electrons to relativistic speeds. These electrons spiral in magnetic fields, emitting radio waves. The Very Large Array in New Mexico and the Atacama Large Millimeter Array, ALMA, in Chile, will monitor Betelgeuse at multiple radio frequencies. The radio brightness and spectrum reveal the magnetic field strength, electron acceleration, efficiency, and density of the surrounding medium. X-ray observations will reveal the hottest material. NASA's Chandra X-ray Observatory and ESA's XMM Newton will image the expanding shockwave and any central neutron star or pulsar. X-rays are emitted by gas heated to millions of degrees. The X-ray brightness and spectrum depend on the shockwave velocity, the density of the surrounding medium, and the composition of the ejector. X-ray observations complement optical data, providing a complete picture of the explosion. If Betelgeuse forms a pulsar, radio and X-ray telescopes will detect it within weeks. Young pulsars are bright in X-rays due to their high surface temperatures and energetic particle winds. Radio emission appears as regular pulses at the rotation frequency. Timing these pulses with millisecond precision allows measurement of the rotation period derivative, and any glitches. The Green Bank Telescope in West Virginia and the Parkes Telescope in Australia are optimized for pulsar searches and will immediately begin monitoring Betelgeuse. Gamma-ray telescopes will detect high-energy emission from radioactive decays and cosmic ray interactions. NASA's Fermi Gamma-ray Space Telescope observes the entire sky every 3 hours. It will track the gamma-ray light curve, which is powered by nickel-5,6 decay. Fermi's data will measure how much nickel was produced, constraining explosion models. Ground-based gamma-ray telescopes, like Veritas and HESS, will search for very high-energy gamma rays from cosmic ray acceleration. Gravitational wave detectors might detect signals if the core collapse is asymmetric. LIGO and Virgo observe gravitational waves from violent events like colliding black holes. A supernova core collapse produces gravitational waves if the collapse is non-spherical. Rotation, magnetic fields, or convective instabilities create asymmetries. The amplitude is small and detection is uncertain, but if successful, it would provide direct information about the collapse dynamics. This would be the first gravitational wave detection from a supernova. The combination of professional and amateur observations across all wavelengths will create the most comprehensive dataset ever collected for a supernova. Previous supernovae were observed with limited instruments. Tycho and Kepler relied on naked eye observations. SN 1987. A had modern detectors but was far away and faint. Betelgeuse will be bright, close, and observed with 21st century technology. The scientific return will be enormous. Data will flow into archives immediately. Astronomers worldwide will analyze it. Papers will be published within days of the explosion. Every aspect of the event will be scrutinized. The light curve, the spectrum, the neutrino burst, the remnant evolution. Models will be tested and refined. Decades of follow-up studies will extract every possible insight. Betelgeuse's supernova will become the benchmark event for core collapse supernovae, referenced in textbooks and lectures for generations. The data will also have practical applications. Understanding supernovae improves our knowledge of stellar evolution, which affects models of galactic chemical evolution. This in turn affects models of planet formation and the emergence of life. Supernovae produce the elements necessary for life. Studying Betelgeuse will refine our understanding of how these elements are created and distributed. In a tangible sense, we are studying our own origins. Could we have prevented it? This question sounds absurd at first. Stars explode due to internal physics operating over millions of years. Human technology cannot affect processes occurring in stellar cores light years away. Yet the question raises interesting theoretical considerations about advanced civilizations and stellar engineering. If a civilization depended on Betelgeuse for survival, could they forestall its death? And what does this question reveal about humanity's relationship with cosmic events? Betelgeuse's core collapse is inevitable given its mass and evolutionary stage. The iron core will reach critical mass, electron degeneracy pressure will fail, collapse will occur. No known physics allows prevention at this stage. Once the core is iron, the countdown has started. The timescale is uncertain, but the outcome is not. However, hypothetical interventions earlier in the star's evolution might alter its fate. One approach would be mass extraction. Red supergiants lose mass through stellar winds, but the rate could theoretically be enhanced. If sufficient mass were removed from the star, the core might never accumulate enough iron to trigger collapse. A star below approximately 8 solar masses will not explode. It will eventually become a white dwarf. If Betelgeuse could be reduced below this threshold, it would avoid supernovae. The engineering challenges are staggering. Betelgeuse has roughly 16 to 19 solar masses. Removing 8 to 11 solar masses requires extracting billions of Earth masses of material. The star's escape velocity at the surface is about 100 kilometers per second. Lifting material against this gravity well requires enormous energy. Even if energy were available, the timescale is problematic. Mass must be removed faster than stellar evolution proceeds, ideally over thousands to millions of years. One speculative method involves using powerful lasers or particle beams to ablate surface material. Directed energy heats a spot on the photosphere, causing gas to expand and escape. This is called photophoresis and is proposed for asteroid deflection. Scaled up dramatically, it might work on stars, but the power requirements are absurd. A continuous petawatt-scale beam operating for millions of years would be needed. This exceeds current human energy production by factors of trillions. Another approach uses magnetic fields. Stellar winds are partially driven by radiation pressure and magnetic activity. Artificially enhancing the star's magnetic field might increase mass loss rates. This requires infrastructure capable of generating magnetic fields comparable to stellar fields across millions of kilometers. Such megastructures are purely theoretical. Even Dyson spheres, hypothetical structures capturing a star's energy output, are beyond current technology by centuries at minimum. A more radical proposal involves inducing premature helium fusion in the outer layers. This would cause the envelope to expand further, cooling it and potentially stabilizing the structure. Fusion could be triggered by injecting deuterium or helium-3 into specific regions. But controlling fusion at stellar scales is impossible with current understanding. The intervention might make things worse, accelerating collapse rather than preventing it. Some theorists suggest that sufficiently advanced civilizations could prevent supernovae not to save the star but to harvest it. A supernova releases 10^44 joules in a few seconds. Capturing even a fraction of this energy would power a civilization for millennia. But capturing energy from an exploding star is far beyond any conceivable technology. The shockwave moves at 30,000 kilometers per second. Material is heated to billions of degrees. Any structure in the vicinity would be vaporized. More realistically, a civilization depending on Betelgeuse would migrate. With sufficient warning, tens of thousands of years, interstellar travel becomes feasible even with modest technological advancement. The civilization could evacuate to other star systems, preserving themselves if not their home star. This is likely the only practical response an advanced civilization could mount. For humanity, Betelgeuse's explosion is not a problem requiring a solution. We do not depend on it. Its light contributes negligibly to Earth's energy budget. The radiation it produces is already factored into background levels. When it explodes, the effects will be scientifically interesting but not existentially threatening. No intervention is necessary or desirable. However, the question prompts consideration of future scenarios. If humanity spreads through the galaxy and establishes civilizations around other stars, stellar evolution becomes relevant. Most stars live billions of years, far longer than civilization timescales. But massive stars like Betelgeuse live only millions of years. A hypothetical colony orbiting a massive star would face an eventual supernova. Planning for this would be essential. Such planning would likely involve relocation rather than prevention. Stellar engineering remains speculative even for advanced civilizations. Moving an entire population to a new star system, while challenging, is conceptually straightforward. Generation ships, suspended animation, or faster-than-light travel if possible, would enable evacuation over centuries or millennia. The civilization would preserve its culture and knowledge, if not its physical location. This highlights a deeper truth. Cosmic events occur on scales that dwarf human concerns. Betelgeuse has been evolving for millions of years. It will become a supernova according to immutable physical laws. Humanity has existed for perhaps 300,000 years, civilization for 10,000. Our entire history is a blink in the star's lifetime. We observe its death not as participants but as witnesses, incapable of influencing the outcome. Yet acceptance does not mean resignation. Science has given us the ability to predict, if not prevent, cosmic events. We know Betelgeuse will explode. We know approximately what the effects will be. This knowledge enables preparation. Monitoring systems to detect the neutrino burst, atmospheric models to predict ozone depletion, communication strategies to manage public response. We cannot stop the supernova, but we can navigate its consequences intelligently. In this sense, the question transforms from "could we prevent it?" to "how do we respond?" The latter is actionable. We respond by gathering data, refining models, educating the public, and ensuring that when Betelgeuse explodes, humanity benefits maximally from the scientific opportunity while minimizing any negative impacts. This is not prevention but mitigation and utilization, making the best of an inevitable event. This philosophy extends beyond Betelgeuse. Asteroids could impact Earth, solar flares could disrupt technology, gamma-ray bursts could threaten the biosphere. None of these can be prevented in the absolute sense, but understanding allows for preparation. The same mindset that studies supernovae develops planetary defense systems, space weather monitoring, and long-term species survival strategies. Acceptance of cosmic indifference motivates proactive response. The long-term effects on Earth's biosphere. While Betelgeuse's immediate effects, optical brightness, neutrino burst, radiation pulse will pass within months, longer-term consequences will unfold over centuries to millennia. The increased cosmic ray flux, ozone depletion, and atmospheric chemistry changes will persist long after the visible supernova fades. Understanding these long-term effects requires examining how ecosystems respond to environmental stresses and how life has adapted to past cosmic events. Earth's biosphere has survived multiple nearby supernovae. Geological and biological evidence suggests several occurred within 1,000 light-years during the past 10 million years. Iron 60 inches ocean sediments, as mentioned earlier, marks these events. The most recent, 2 to 3 million years ago, coincided with the Pliocene-Pleistocene boundary, a period of significant climate change and faunal turnover. Some researchers propose that supernova radiation contributed to these changes, though direct causation is debated. The mechanism would be ozone depletion. Cosmic rays and gamma rays produce nitrogen oxides in the stratosphere. These compounds catalyze ozone destruction. Reduced ozone allows more ultraviolet radiation to reach the surface. UV damages DNA, particularly at wavelengths around 260 nanometers. Organisms exposed to elevated UV experience increased mutation rates, cancer, and developmental problems. Marine ecosystems are especially vulnerable. Phytoplankton, microscopic algae forming the base of the ocean food web, live near the surface where sunlight penetrates. They require light for photosynthesis but are sensitive to UV. A 20 to 40% increase in UV could reduce phytoplankton productivity. This would cascade through the food web. Zooplankton that feed on phytoplankton would decline. Fish that eat zooplankton would decline. Marine mammal and seabird populations would drop. Commercial fisheries would suffer. Betelgeuse is farther away than the supernovae likely responsible for past biosphere disturbances. Those were estimated at 50 to 150 light-years away. Betelgeuse at 642 light-years will deliver far less radiation. The effects will be detectable but not catastrophic. Modern simulations predict a 10 to 30% UV increase at the surface for a few years, followed by longer-term ozone depletion, causing a 20 to 50% UV increase lasting decades. For terrestrial ecosystems, these UV levels are manageable. Plants have adaptations, protective pigments, leaf structures that minimize UV exposure, DNA repair mechanisms. Animals can seek shade, adjust behavior to avoid midday sun, or evolve protective coloration. Humans can use sunscreen, clothing, and architectural shade. The adaptations are not cost-free. They require energy and resources that could otherwise go to growth or reproduction, but they work. The greater concern is for organisms that cannot easily avoid UV. Amphibians, which have permeable skin, are particularly vulnerable. Frog and salamander populations might decline if UV stress compounds other threats like habitat loss and pollution. Insects, especially those with aquatic larval stages, could be affected. Pollinators like bees, already under stress from pesticides and disease, might face additional pressure. Coral reefs face combined stressors. Corals are sensitive to UV and also to temperature changes. The supernova's atmospheric effects might alter weather patterns, potentially affecting ocean temperatures. Coral bleaching events, where corals expel their symbiotic algae due to stress, could become more frequent. Reef ecosystems support enormous biodiversity. Their decline would have cascading effects on marine environments. Agricultural impacts are predictable and manageable. Crops vary in UV sensitivity. Some, like rice and wheat, are relatively resistant. Others, like soybeans and certain vegetables, are more sensitive. Yields could decrease by 10 to 20% without intervention. But agricultural science has developed UV-resistant cultivars through selective breeding and genetic modification. These could be deployed if Betelgeuse explodes, mitigating yield losses. Alternatively, shade structures, though expensive, could protect sensitive crops. The cosmic ray increase poses a different challenge. Cosmic rays at Earth's surface primarily produce muons, subatomic particles that penetrate deeply into matter. Muons pass through living tissue, occasionally ionizing molecules and damaging DNA. The effect is small compared to other radiation sources like radon or medical X-rays, but a sustained increase accumulates over lifetimes. Human cancer rates might increase by a fraction of a percent. This translates to thousands of additional cases globally per year if cosmic ray flux doubles. For perspective, background cancer risk is roughly 40% in developed nations. A 1% increase makes it 40.4%. Individually imperceptible but statistically significant across large populations, health systems would need to account for increased cancer burden, expanding screening and treatment capacity. Cosmic rays also affect electronics. High-energy particles can flip bits in computer memory, causing errors. This is already a concern for satellites and aircraft electronics. The effect is called a single-event upset. A sustained increase in cosmic ray flux would increase the frequency of these errors. Redundant systems and error-correcting codes mitigate the problem, but costs rise. Satellite lifespans might decrease. More frequent replacements would strain space launch capacity. The long-term climate effects are uncertain. Cosmic rays influence cloud formation through ionization of the atmosphere. More ionization means more cloud condensation nuclei, leading to more clouds. Clouds reflect sunlight, cooling the planet. This cosmic ray climate connection is called the Svensmark effect, proposed by Danish physicist Henrik Svensmark in the 1990s. It remains controversial, with some studies supporting it and others finding no significant correlation. If the Svensmark effect is real and strong, increased cosmic rays from Betelgeuse could cool Earth's climate over centuries. The magnitude would depend on the cosmic ray increase and the strength of the cloud ionization feedback. Estimates suggest a cooling of 0.1 to 0.5 degrees Celsius over decades to centuries. This is comparable to natural climate variability and much smaller than anthropogenic warming, currently exceeding 1 degree Celsius and projected to reach 2 to 4 degrees by 2100. However, any cooling from cosmic rays would be temporary. Once the supernova remnant disperses and cosmic ray flux returns to normal, temperatures would rebound. The net effect might be a slight delay in warming trends, but not a permanent change. Climate policy should not count on supernovae to offset greenhouse gas emissions. The timing is unpredictable and the effect modest. One overlooked benefit is increased awareness of cosmic hazards. Betelgeuse's supernova will be a visceral demonstration that Earth exists in a dynamic, sometimes hostile universe. This awareness could motivate investment in planetary defense, space weather monitoring, and long-term species survival strategies. The supernova might serve as a wake-up call, spurring action on issues that often seem abstract or distant: asteroid defense, diversifying human settlements beyond Earth, maintaining biodiversity as insurance against catastrophic events. When might it actually happen? The single most common question about Betelgeuse is, when will it explode? The frustrating, honest answer is, we do not know. It could happen tonight. It could happen in 100,000 years. Stellar evolution models cannot predict the exact timing. Understanding why requires examining what we know about Betelgeuse and the limitations of current models. Betelgeuse's mass is estimated at 16 to 19 solar masses, based on its luminosity and temperature. This places it firmly in the supernova range. Stars above roughly 8 solar masses end as supernovae. Stars below that become white dwarfs. Betelgeuse will definitely explode. The question is when. But which phase is Betelgeuse actually in? We cannot observe the core directly. The photosphere, the visible surface, reveals temperature and composition of the outer layers, but nothing about the core. The star's radius, luminosity, and surface oscillations provide indirect clues, but interpretation requires models. Different models give different answers. Asteroseismology of Betelgeuse suggests a large convective core currently burning helium or carbon. The data is consistent with an age of 8 to 10 million years and a supernova timeline of 10,000 to 100,000 years. But uncertainties are large. The oscillation data is complex and difficult to interpret. Multiple models fit the observations. Narrower constraints require better data, which requires more sensitive instruments and longer observation periods. Recent studies using high-resolution imaging have revealed additional structures. In 2020, the Atacama Large Millimeter Array, ALMA, observed Betelgeuse's surface directly, resolving details smaller than the star's radius. The images showed a large, bright spot covering a significant fraction of one hemisphere. This was interpreted as a massive convective cell, a hot bubble rising from the interior. The size and brightness of the cell suggest vigorous convection, consistent with late-stage evolution. The 2019 to 2020 dimming event provided unique data. As Betelgeuse dimmed by 60%, astronomers monitored it intensively. Spectroscopy revealed that the dimming was caused by dust, not by a change in the star's intrinsic brightness. This ruled out supernovae as the immediate cause, but the event demonstrated that Betelgeuse is highly active, capable of ejecting massive amounts of material suddenly. Such activity is characteristic of stars nearing the end of their lives. Statistical arguments provide another perspective. Surveys of red supergiants in other galaxies show that stars similar to Betelgeuse spend roughly 10,000 to 100,000 years in the red supergiant phase. This phase begins after helium burning in the core and ends with core collapse. Betelgeuse exhibits all the characteristics of a mature red supergiant, suggesting it is somewhere in this time window. But somewhere spans 5 orders of magnitude from today to 100,000 years hence. One complicating factor is rotation. Massive stars rotate, and rotation affects evolution. Fast-rotating stars mix material between core and envelope more efficiently. This prolongs nuclear burning and delays core collapse. Slow-rotating stars stratify, with distinct layers that do not mix. This shortens the time to supernova. Betelgeuse's rotation rate is uncertain. Observations suggest a surface rotation period of about 1 year, but the core might rotate faster or slower. Mass loss also complicates predictions. Red supergiants lose mass through stellar winds at rates of 10, -6 to 10, -4 solar masses per year. The exact rate depends on luminosity, temperature, and poorly understood processes like convection and magnetic fields. Betelgeuse's mass loss rate is measured at roughly 10, -6 solar masses per year, but this varies over time. The 2020 dimming event involved mass loss temporarily spiking higher. Higher mass loss means the star sheds its envelope faster. This could either hasten or delay supernovae, depending on how much mass is lost and when. If the envelope is removed before the core reaches critical mass, the star might avoid supernova entirely, becoming a helium star that eventually collapses without a bright optical display. Alternatively, mass loss might trigger instabilities that accelerate core evolution. The interplay between mass loss and core burning is complex and incompletely understood. Binary interactions add another layer of uncertainty. Some researchers have proposed that Betelgeuse might have a companion star, though no companion has been definitively detected. If a companion exists, gravitational interactions could affect Betelgeuse's rotation, mass loss, and envelope structure. Binary systems evolve differently than isolated stars. The companion could strip material from Betelgeuse, altering its evolutionary path. Or Betelgeuse could have already absorbed a companion in the past, affecting its current properties. Given all these uncertainties, the best answer to when is probabilistic. The likelihood of a supernova increases with time. A supernova tomorrow is extremely unlikely, but not impossible. A supernova within the next 100 years is improbable. Within 10,000 years is plausible. Within 100,000 years is likely. But these are rough estimates, not precise predictions. Some astronomers propose monitoring Betelgeuse for precursor signs. Theoretical models suggest that in the final years before collapse, the star should exhibit increased variability, enhanced mass loss, or changes in surface composition as core processed material reaches the envelope. If such signs appear, they could provide weeks to years of warning. But this assumes precursors exist and are detectable, both of which are uncertain. The neutrino burst will provide definitive warning, but only hours in advance. When core collapse begins, neutrinos escape immediately. Neutrino detectors on Earth will register the burst roughly 10 seconds after it occurs, 642 years after it actually happened. This is sufficient warning to alert optical telescopes, but insufficient for long-term preparation. For practical purposes, astronomers treat Betelgeuse as a star that could explode at any time. Monitoring programs track its brightness, spectrum, and surface features continuously. Instruments are tested and calibrated to ensure readiness. Communication protocols are established so that when the neutrino burst is detected, the global astronomical community can respond within minutes. This preparedness is the best we can do given current knowledge. The uncertainty also presents an opportunity. When Betelgeuse does explode, it will provide a natural experiment testing stellar evolution models. The supernova's properties, brightness, spectrum, remnant characteristics will reveal Betelgeuse's mass, composition, and evolutionary state at the moment of collapse. Comparing these observations with model predictions will validate or refute current theories. Every discrepancy will point toward missing physics or incorrect assumptions, driving progress. In this sense, not knowing when Betelgeuse will explode is part of the scientific process. Uncertainty motivates observation and modeling. As data accumulates, models improve, predictions narrow. Eventually, future theories might predict supernova timing to within decades for specific stars. Betelgeuse, by exploding at an unknown time, will help develop those future theories. The ignorance is temporary. The knowledge gained will be permanent. The explosion we are waiting for, somewhere between this sentence and 100,000 years from now, Betelgeuse will explode. The iron core will collapse. Neutrinos will stream outward. A shockwave will tear through the star's envelope. The visible star will brighten beyond Venus, beyond the crescent moon, becoming a beacon visible even in daylight. For weeks, Orion will be transformed, the familiar constellation unrecognizable with a brilliant point replacing the red giant's shoulder. This is not speculation, it is a certainty. The physics is understood, the time scale is uncertain, but the outcome is not. Betelgeuse will become a supernova. And when it does, humanity, if humanity still exists, will witness an event that no human has seen at this proximity. The last comparable supernova visible from Earth occurred in 1604. 4 centuries have passed. Generations have lived and died without seeing a new star appear. The scientific community is ready. Instruments are prepared. Protocols are established. When the neutrino burst arrives, alerts will go out within minutes. Telescopes around the world will turn to Betelgeuse. Observations will begin immediately and continue for years. The data will fill archives, fuel dissertations, and populate textbooks. Every aspect of the event will be studied, analysed, modelled, and debated. But beyond science, the explosion will be a cultural moment. A generation will remember where they were when Betelgeuse exploded. Artists will create, writers will reflect, philosophers will interpret. The event will become part of human history, like comets and eclipses and auroras, a reminder that Earth exists within a dynamic cosmos. For now, Betelgeuse shines in winter skies, red and variable, marking Orion's shoulder. It appears stable, eternal, unchanging from night to night. Only sensitive instruments detect the slow brightening and dimming, the convective cells rising and falling, the mass loss that bleeds the star into space. To casual observers, Betelgeuse is just another star, perhaps slightly brighter than most, noticeably redder than its neighbours. This appearance is deceptive. Beneath the photosphere, a massive star is dying. The core is iron. Fusion has stopped. Only electron degeneracy pressure prevents collapse, and that pressure is finite. The countdown has begun, though we do not know how much time remains on the clock. Hours, millennia, the uncertainty does not change the outcome. When collapse begins, it will proceed rapidly. The core will shrink from Earth size to city size in less than a second. Temperatures will soar. Neutrinos will escape. The shockwave will form and propagate. Hours later, the first optical photons will emerge from the photosphere. The star will begin to brighten. Within days, it will be unmistakable. Within weeks, it will dominate the night sky. Humanity will watch, through telescopes and instruments, but also with naked eyes. People will step outside and look up, seeing with their own eyes what no one alive has seen, a supernova. A stellar explosion, the death of a star. This direct visual experience, unmediated by technology, will connect observers to the cosmos in ways that photographs and data cannot. Children will ask questions. What is happening? Why is there a new star? Is it dangerous? Parents will explain, drawing on whatever knowledge they possess. Science educators will be in demand. The media will cover the story extensively. For a brief moment, astronomy will dominate public consciousness in ways it rarely does. The brightness will fade. After weeks, Betelgeuse will dim below the moon's brightness. After months, it will be just another bright star. After years, visible only through binoculars. After decades, requiring a telescope, the supernova remnant will persist, visible to professional instruments for millennia. But to casual observers, the event will be a memory, a story to tell future generations. I saw Betelgeuse explode. This is what we are waiting for. Not an abstract event described in papers, but a real, visible transformation of the night sky. A reminder that the universe is not static. Stars are born, evolve, and die. The elements they create seed new worlds. Life arises on some of those worlds. That life looks up, sees the stars, and wonders. The cycle continues, driven by processes operating since the first stars ignited billions of years ago. Betelgeuse is one node in this cycle. Its atoms were forged in earlier stars. Its death will create atoms that form future stars. The specific atoms that comprise Betelgeuse right now, the hydrogen in its envelope, the iron in its core, the oxygen, carbon, and nitrogen throughout, will be scattered across light years. Some will drift in space for millions of years. Some will be incorporated into molecular clouds. Some will become part of planets where, perhaps, life will arise and wonder about the universe that created it. This continuity, this recycling of matter and energy, is the deepest truth Betelgeuse reveals. Nothing is permanent. Stars explode. Galaxies collide. The universe evolves. But the atoms persist, rearranged into new forms, participating in new stories. The explosion we are waiting for is not an ending, it is a transformation. Betelgeuse the red supergiant will become Betelgeuse the supernova, then Betelgeuse the remnant, and finally Betelgeuse the dispersed atoms mixed into the interstellar medium, indistinguishable from countless other atoms, from countless other dead stars. In this sense, Waiting for Betelgeuse to explode is waiting for the universe to reveal itself, waiting for a demonstration of processes usually too slow or too distant to observe, waiting for confirmation that the equations work, that our understanding is correct, that reality operates as predicted, and waiting, perhaps, for a moment of cosmic perspective when the sky itself reminds us that we live in a universe of unimaginable scale, violence, and beauty. The explosion is coming, not soon by human standards, but soon enough that current instruments will detect it. The data will be analyzed, the models will be refined, science will advance. And when the light finally fades, when the remnant disperses, when the atoms mix into the galactic background, Betelgeuse will be gone. But what it taught us about stars, about physics, about our place in the cosmos will remain. Knowledge, unlike matter, does not decay. It accumulates, generation after generation, building toward a comprehensive understanding of the universe and our place within it. This is the real meaning of Betelgeuse's explosion. Not danger or disaster, but discovery. Not an end, but a continuation. The universe is evolving, and we are watching, learning, and carrying forward the knowledge into whatever future awaits. The supernova is coming, and we will be ready. The night sky after Betelgeuse. When the supernova finally fades, a process taking years to decades, the night sky will be permanently altered. Orion, one of the most recognizable constellations in human history, will never look the same again. The distinctive pattern that has guided sailors, marked seasons, and inspired countless myths across every culture will have changed within a single human lifetime. This transformation carries implications beyond astronomy, touching navigation, culture, and our collective relationship with the cosmos. Betelgeuse currently marks Orion's eastern shoulder with a distinctly red hue, magnitude plus 0.5 on average. Its color contrasts sharply with the blue-white stars surrounding it. Rigel at the opposite corner, the belt stars Alnitak, Alnilam, and Mintaka, and the sword stars beneath. This color contrast makes Orion visually striking and easy to identify. Remove Betelgeuse, and the constellation loses a defining feature. The supernova remnant will initially be brighter than the original star. For the first year, it may glow at magnitude +1 or +2, visible to the naked eye. This creates an odd situation. Orion temporarily has an extra bright star. Star charts will need updating. Planetarium programs will require patches. Navigation guides, using Orion as a reference, will note the change. The transition period, where the supernova is bright but no longer the familiar red giant, will create confusion for casual observers. As decades pass, the remnant will dim below naked eye visibility. Orion will then have a gap. Where Betelgeuse once glowed, there will be nothing apparent to unaided eyes. The constellation will appear lopsided, unbalanced. For observers learning the night sky, this absence will be unremarkable. They never knew Betelgeuse. But for those who remember the original pattern, the sky will seem incomplete, like a familiar painting with one element erased. This psychological impact should not be underestimated. Humans are pattern recognition creatures. We group stars into constellations, assign them names and stories, and use them as mnemonic devices. These patterns become embedded in memory and culture. Changing them feels wrong on an intuitive level, even when intellectually we understand that stars are not fixed. The night sky is supposed to be eternal, unchanging, reliable. Betelgeuse's disappearance challenges this assumption viscerally. Navigators have used Orion for millennia. The constellation is visible from nearly every inhabited location on Earth, spanning latitudes from 85 degrees N to 75 degrees S. Its position relative to the celestial equator makes it a reliable reference for finding cardinal directions. Betelgeuse specifically marks true north when the constellation is oriented correctly. Navigation courses and survival manuals include Orion-based techniques. These will remain valid. Rigel and the belt stars provide sufficient references, but institutional knowledge based on Betelgeuse will become obsolete. Mythology and storytelling will face a dilemma. Orion myths exist in Greek, Roman, Egyptian, Mesopotamian, Native American, Australian, Aboriginal, and countless other traditions. Many reference specific stars. Some identify Betelgeuse as the hunter's shoulder or hand. Others incorporate its red colour into the narrative. When the star disappears, do these stories change? Do we alter myths that have persisted for thousands of years to match the new sky? Or do we preserve them as historical artifacts, accepting that they describe a sky that no longer exists? Astrology faces similar questions. Western astrology rarely uses Betelgeuse specifically, focusing on planets and zodiacal constellations. But other astrological traditions do incorporate fixed stars. Chinese, Hindu, and Arabic astrology all reference specific bright stars in their systems. Betelgeuse appears in some of these traditions. Its disappearance will require either ignoring the change, reinterpreting its meaning, perhaps the supernova remnant replaces the star, or acknowledging that celestial references in astrology are time-dependent rather than eternal. For astronomy education, Betelgeuse's supernova is a gift. Textbooks often describe stellar evolution abstractly, showing diagrams of the HR diagram with arrows indicating evolutionary paths. Students memorize that massive stars become red supergiants and then supernovae, but it remains theoretical. Betelgeuse will make it concrete. Future astronomy students will study a supernova that occurred within human memory. With comprehensive data available, the event will become a touchstone, referenced repeatedly as the best observed core collapse supernova in history. Orion will eventually regain familiarity. A generation will grow up with the constellation as it appears post-supernova. For them, the absence of Betelgeuse will be normal. They will learn constellations using the altered pattern. When shown historical images with Betelgeuse present, they will find it strange, like seeing a restored version of a faded photograph. The sky they know will be the sky without the red giant. But the supernova remnant, though invisible to naked eyes, will remain astronomically prominent for millennia. Radio telescopes will detect synchrotron emission. X-ray observatories will image the expanding shockwave. Optical telescopes will track the filamentary structure as it evolves. The remnant will be studied as intensely as the Crab Nebula, becoming a standard reference object for supernova physics. Every student learning about supernova remnants will study Betelgeuse as a primary example. Other stars will eventually take Betelgeuse's place in cultural consciousness. Perhaps Rigel, already the brightest star in Orion, will become the constellation's defining feature, or the belt stars, which form such a distinctive asterism. Human culture is adaptable. We will create new patterns, new stories, new navigation techniques. The sky will be different, but still useful, still beautiful, still inspiring. This impermanence is troubling to contemplate. We want the sky to be eternal, a fixed backdrop against which human dramas play out, but astronomy reveals that everything is temporary. Stars form, shine, and die. Galaxies collide and merge. Even atomic nuclei decay given enough time. The universe is not a static stage but a dynamic process, constantly changing at every scale. Betelgeuse's supernova, by altering a familiar constellation, forces this realization upon us in an immediate, visceral way. Yet there is beauty in impermanence. A sky that never changed would be boring, ultimately. Change makes moments precious. The night sky with Betelgeuse is a specific configuration that has existed for thousands of years but will not persist. Those who observe it now are witnessing a temporary arrangement, soon to transform. This creates a kind of cosmic nostalgia, appreciating what we have while it lasts, knowing it will not last forever. The scientific papers that will follow. When Betelgeuse explodes, the scientific literature will be flooded with papers. Within hours of the neutrino detection, preprints will appear on RxIV, the online physics repository. Dozens the first day, hundreds within a week, thousands over the following year. The supernova will generate more publications than any single astronomical event in history. Understanding this expected flood of research helps appreciate the scale of scientific investment in studying the explosion. The first papers will be rapid response observations. Telescopes that captured Betelgeuse immediately after the neutrino alert will publish light curves showing the initial brightening. These papers will be brief, presenting data with minimal analysis. The goal is establishing observational facts: when the brightening started, how fast it rose, what the initial spectrum showed. Priority goes to speed, getting information into the community as quickly as possible, so other researchers can plan observations and adjust models. Within days, theoretical papers will appear. Modelers will run simulations trying to match the observed light curve. These early models will be rough, using generic red supergiant parameters. But they will establish whether the explosion looks like standard core collapse models or shows unexpected features. Any deviations from prediction will be highlighted, guiding further observations. If the light curve rises faster than expected, that suggests one set of conditions. Slower rise suggests different conditions. Each possibility directs observers towards specific follow-up measurements. Spectroscopic papers will follow. Spectra reveals chemical composition, temperature, density, and velocity of the ejected material. Early spectra will be dominated by hydrogen from the envelope. As the supernova evolves, deeper layers become visible. Carbon, oxygen, silicon, and iron lines appear. The relative strengths of these lines constrain how much of each element was produced. Comparing nucleosynthesis models tests our understanding of fusion reactions in massive stars. Neutrino papers will be among the most important. Every neutrino detector that recorded the burst will be published. Super Kamiokande will have the most data, likely 50 to 100 events. IceCube will have fewer, but provides independent confirmation and different systematic uncertainties. Comparing datasets from multiple detectors allows testing for neutrino oscillations, the quantum mechanical phenomenon where neutrinos change flavor as they travel. The neutrino burst's timing structure encodes information about core collapse dynamics. If the burst is smooth, it suggests the collapse proceeded straightforwardly. Core collapsed, neutron star formed, neutrinos escaped over a few seconds. If the burst shows structure multiple peaks, a sharp cutoff, an extended duration, it indicates complications. Multiple peaks might suggest oscillations in the proto-neutron star. A sharp cutoff could indicate black hole formation. Extended duration might reveal fallback accretion. The neutrino energy spectrum is equally informative. Higher energy neutrinos come from hotter regions near the core. Lower energy neutrinos come from cooler outer regions. The spectrum shape reveals the temperature profile of the proto-neutron star. This constrains the equation of state of neutron-rich matter, which governs neutron star structure. Laboratory experiments cannot access these densities and temperatures. Supernova neutrinos provide the only direct probe. Radio observations will track the shockwave's interaction with circumstellar material. As the shockwave sweeps outward, it heats gas that Betelgeuse ejected over millions of years. This gas emits radio waves. The intensity and spectrum depend on gas density and magnetic field strength. Radio observations map the circumstellar environment in 3 dimensions, revealing the star's mass loss history. X-ray observations complement radio data. X-rays come from hotter gas deeper in the shockwave. X-ray imaging shows fine structure, filaments, knots, and clumps where the shockwave is moving faster or slower. These structures form because the circumstellar medium is not uniform. Variations in density create Rayleigh-Taylor instabilities, where fast-moving, low-density material overtakes slow-moving, high-density regions. The patterns that develop are complex and beautiful, captured in false color images that reveal physics invisible to optical telescopes. Infrared observations track dust formation. Within weeks of the explosion, the ejected material cools enough for dust grains to condense. These grains are composed of silicates, carbon, or metals, depending on local composition and temperature. Dust absorbs optical light and emits it in infrared. The infrared spectrum identifies grain composition. The brightness indicates how much dust formed. This is crucial data for understanding how supernovae contribute to interstellar dust, which is essential for planet formation. Polarimetry papers will analyze light polarization from the supernova. Polarization arises from asymmetry in the explosion. If the supernova were perfectly spherical, light would be unpolarized. Deviations from spherical symmetry create polarization. Measuring polarization across the spectrum reveals the explosion's geometry. Was it slightly asymmetric or highly aspherical? Did material eject preferentially along the rotation axis? Polarization data constrains explosion models and tests whether rotation, magnetic fields, or instabilities dominate. Chemical abundance papers will appear months after the explosion, once spectroscopy becomes detailed enough to measure specific isotope ratios. Different nucleosynthesis processes produce different isotopes. The ratio of nickel 5,6 to iron 5,6 tests fusion models. The presence of radioactive isotopes like cobalt 60 or titanium 44 indicates specific burning conditions. Trace elements like zinc, germanium, and selenium reveal neutron capture processes. Every isotopic measurement refines our understanding of nuclear physics under extreme conditions. Distance papers will be published, refining Betelgeuse's distance using supernova data. The expanding photosphere method uses the supernova's brightness and expansion velocity to calculate distance geometrically. The more precisely we know the distance, the more accurately we can convert observed brightness to intrinsic luminosity. Luminosity constrains the amount of radioactive nickel produced, which constrains the explosion energy and progenitor mass. The remnant papers will begin within weeks and continue for decades. As the expanding ejector interacts with surrounding material, the remnant evolves. Its structure changes, its spectrum shifts, its brightness dims. Tracking this evolution tests models of supernova remnant physics. How does the shockwave transfer energy to surrounding gas? How efficient is cosmic ray acceleration? How do instabilities develop? Each observation adds data points to these questions. If Betelgeuse forms a pulsar, entire subfields will mobilize. Pulsar timing papers will measure the rotation period to microsecond precision, tracking spin down over years. Glitch papers will report sudden increases in rotation speed as the crust readjusts. Emission mechanism papers will analyze the radio, optical, and X-ray pulses, testing models of pulsar magnetospheres. Pulsar wind nebula papers will study the shocked region where the pulsar's relativistic wind collides with supernova ejecta. Gravitational wave papers will be published regardless of whether a signal is detected. LIGO and Virgo will analyze data from the time of core collapse. If a signal is found, it will be revolutionary, providing direct information about asymmetries during collapse. If no signal is found, that constrains how symmetric the collapse was. Upper limits on gravitational wave amplitude restrict possible models. Either outcome is scientifically valuable. In the long term, Betelgeuse papers will continue appearing for decades. Every few years, a new instrument or technique will enable novel observations. When the James Webb Space Telescope's successor launches, it will observe Betelgeuse's remnant. When next-generation neutrino detectors come online, they will be calibrated using Betelgeuse data. When gravitational wave detector sensitivities improve, the archived gravitational wave data from Betelgeuse's collapse will be reanalyzed at higher precision. The communications blackout nobody talks about. When Betelgeuse explodes, everyone focuses on the spectacle, the bright new star, the neutrino burst, the radiation. But there's a quieter consequence that will disrupt modern civilization in ways most people haven't considered. A prolonged disruption to global communication systems that could last years, not days. The problem isn't the initial blast, it's what comes after. The supernova will inject enormous quantities of ionized particles into Earth's upper atmosphere, specifically the ionosphere, the layer between 50 and 600 kilometers altitude that reflects radio waves and enables long-distance communication. When high-energy photons and cosmic rays from Betelgeuse strike this region, they'll dramatically increase ionization levels, fundamentally altering how radio signals propagate. Radio communication relies on predictable ionospheric behavior. AM radio, shortwave broadcasts, aviation communication, maritime navigation, and even some military systems depend on radio waves bouncing off the ionosphere at consistent angles. When ionization increases, the reflection height changes. Signals that normally reach their destination might skip over it entirely or be absorbed before arrival. The effect resembles trying to communicate during a solar storm, but sustained over months or years rather than hours. Satellite communications face different challenges. The increased ionization will affect GPS signals as they pass through the atmosphere. GPS works by measuring the precise time it takes signals to travel from satellites to receivers. The ionosphere naturally delays these signals, but the delay is predictable and corrected by algorithms. A dramatically altered ionosphere means those corrections become inaccurate. Position errors could increase from meters to tens of meters, enough to disrupt precision agriculture, surveying, autonomous vehicles, and navigation systems worldwide. The supernova's ultraviolet radiation will also enhance the D region of the ionosphere, the lowest layer that normally absorbs high-frequency radio waves. Enhanced D region absorption could black out shortwave communications for weeks during daylight hours. This affects remote regions that depend on shortwave radio parts of Africa, South America, and the Pacific Islands, where internet infrastructure remains limited. For these communities, Betelgeuse's explosion could mean prolonged communication isolation. Aviation will face operational challenges. Aircraft flying over oceans and polar regions rely on high-frequency radio for communication with ground control. When those frequencies become unreliable, airlines must reroute flights to stay within satellite communication range, increasing fuel costs and travel times. Polar routes connecting North America to Asia could become temporarily unviable, forcing aircraft to take longer, more expensive paths. The space industry will feel immediate impacts. Satellite operators will need to adjust orbital calculations more frequently as atmospheric drag increases. The heated, expanded upper atmosphere creates more resistance, causing satellites in low Earth orbit to lose altitude faster than normal. The International Space Station will require more frequent reboost maneuvers to maintain its orbit. Small satellites without substantial propulsion systems might deorbit prematurely, creating space debris as they descend. Ground-based astronomy will also suffer. Increased atmospheric ionization creates additional scintillation, the twinkling effect that distorts observations. Radio telescopes will detect enhanced background noise, reducing their sensitivity. Optical telescopes will contend with increased air glow as atmospheric molecules excited by the supernova's radiation emit their own light. Ironically, the most important astronomical event in centuries will temporarily degrade our ability to observe the rest of the universe. The economic costs accumulate quickly. Telecommunications companies will spend billions adapting infrastructure. GPS-dependent industries from precision farming to package delivery will face reduced efficiency. Aviation fuel costs will rise. Satellite operators will launch replacement satellites sooner than planned. The total economic impact could reach hundreds of billions of dollars spread over several years. Mitigation is possible, but expensive. Communication systems could shift to frequencies less affected by ionospheric changes. Satellite constellations could be adjusted to provide redundant coverage. Ground-based navigation systems like Orion could be expanded as GPS backups. But these adaptations require time and investment that might not materialize until the problem becomes acute. Historical precedent exists, though on smaller scales. The 1859 Carrington event, a massive solar storm, disrupted telegraph systems worldwide. Operators reported equipment sparking and catching fire. Telegraph messages could be sent with batteries disconnected, powered purely by induced currents. A Betelgeuse supernova won't create effects that dramatic, but the sustained nature of the disruption months to years rather than hours to days presents unique challenges that a solar storm doesn't. Scientists are developing contingency plans. Space weather forecasting centers are modeling how different supernova scenarios would affect Earth's atmosphere. Communication protocols are being tested for high ionization environments. Satellite designs are incorporating more resilient components. But comprehensive preparation requires acknowledging that a supernova at Betelgeuse's distance isn't just a visual spectacle. It's a sustained assault on the invisible infrastructure modern civilization depends upon. The irony is profound. Betelgeuse's explosion will be the most observed astronomical event in human history, generating unprecedented scientific data. Yet that same event will temporarily impair the communication systems scientists use to share their discoveries. The supernova that connects us to cosmic processes will simultaneously disrupt the technology connecting us to each other, the astronomical revolution that follows. When Betelgeuse explodes, it won't just illuminate the night sky, it will revolutionize astronomy itself. For the first time in human history, scientists will observe a nearby supernova with modern instruments across every wavelength, generating data that will rewrite textbooks and resolve debates that have persisted for decades. The scientific return will be so enormous that careers will be built analyzing this single event for generations. Consider the sheer volume of data. Every major telescope on Earth and in space will observe Betelgeuse continuously. The James Webb Space Telescope will capture infrared spectra revealing the supernova's chemical composition in unprecedented detail. The Event Horizon Telescope network, which imaged the black hole in M87, will attempt to resolve structures within the expanding debris cloud. Radio telescope arrays will track the Shockwave as it sweeps through Betelgeuse's circumstellar material. X-ray observatories will monitor the newborn neutron star or black hole. Within hours of the explosion, petabytes of data will begin accumulating more information about a single supernova than exists for all previous supernovae combined. Neutrino detection alone will transform particle physics. Super Kamiokande in Japan will record 50 to 100 neutrino events over 10 seconds, enough to measure the neutrino energy spectrum with unprecedented precision. This data will constrain the equation of state of neutron-rich matter, something impossible to test in terrestrial laboratories. The neutrino burst's timing structure will reveal whether core collapse proceeded smoothly or encountered complications, bounces, convection, or even black hole formation. Neutrino oscillations, the quantum mechanical phenomenon where neutrinos change flavor during travel, can be measured directly by comparing detection rates at different observatories. These measurements will test the standard model of particle physics in ways that accelerator experiments cannot. Gravitational wave astronomy might achieve its first supernova detection. LIGO and Virgo continuously monitor space-time for ripples from violent cosmic events. Core collapse supernovae produce gravitational waves if the collapse is asymmetric, if rotation, magnetic fields, or convective instabilities create departures from perfect spherical symmetry. The amplitude will be small, near the edge of detectability, but Betelgeuse's proximity gives a fighting chance. Detection would provide direct information about processes occurring deep inside the collapsing core, inaccessible to any other observation. Even a non-detection sets important upper limits on asymmetry, constraining models of stellar core collapse. The supernova's light curve brightness over time will become the benchmark for all future supernova studies. Current models predict peak brightness, decline rate, and color evolution. But these predictions rely on observations of distant supernovae where details are lost. Betelgeuse will be close enough to resolve changes hour by hour, day by day, with precision impossible for any previous event. Deviations from predictions will highlight missing physics in current models. The radioactive decay of nickel-5,6 powers the optical display. Measuring the light curve precisely determines how much nickel was synthesized during the explosion, directly testing nucleosynthesis theory. Spectroscopy will reveal the supernova's chemical composition in detail no previous event has provided. Early spectra will show hydrogen from the envelope. As the ejecta expand and thin, deeper layers become visible: helium, carbon, oxygen, silicon, iron. The relative strengths of emission lines reveal how much of each element was produced. Velocity measurements from Doppler shifts show how fast different layers are moving. Asymmetries in the spectrum indicate that the explosion wasn't spherical, that material ejected in some directions faster than others. This information tests theoretical models of how massive stars explode and how they synthesize elements. The supernova remnant's evolution will be monitored for centuries. Within years, the expanding debris will begin interacting with circumstellar material ejected by Betelgeuse during its red supergiant phase. This interaction produces shockwaves that accelerate particles to cosmic ray energies. Radio, X-ray, and gamma-ray observations will trace this process, testing theories of how supernovae accelerate particles and where cosmic rays originate. Optical telescopes will image filamentary structures as the ejecta become transparent, revealing three-dimensional structure. The remnant will become the most studied supernova remnant in existence, displacing the Crab Nebula as the primary reference object. If Betelgeuse's core forms a pulsar, radio astronomers will immediately begin timing observations. Young pulsars rotate rapidly, periods of milliseconds to seconds, and slow down measurably over years. Timing a pulsar near Betelgeuse will measure its rotation period, spin-down rate, magnetic field strength, and any glitches, sudden speed-ups when the neutron star's crust readjusts. This data constrains neutron star structure and tests models of how pulsars emit radiation. If the pulsar is visible in X-rays, it will be the nearest and brightest such object, allowing detailed studies of pulsar winds and magnetospheres. The explosion will also resolve long-standing questions about stellar evolution. How do massive stars lose mass during their final stages? What determines whether a core collapses to a neutron star or black hole? How asymmetric are supernova explosions? Current answers rely on models and observations of distant events. Betelgeuse will provide direct measurements, removing much of the uncertainty. Stellar evolution theory will be calibrated against a real, nearby example, rather than statistical averages from distant populations. Amateur astronomers will contribute significantly. The supernova will be visible in small telescopes, even binoculars, allowing thousands of observers worldwide to monitor brightness changes continuously. Professional telescopes cannot observe Betelgeuse every night; they have other commitments. Amateurs can fill those gaps, providing continuous coverage that professionals alone cannot achieve. Citizen science projects will coordinate these observations, creating a global network monitoring the supernova around the clock. This democratization of astronomy, where enthusiasts contribute to cutting-edge research, will inspire a generation of future scientists. Educational impact will be profound. Students at every level, from elementary school to graduate programs, will study Betelgeuse's supernova. Textbooks will be rewritten to include real data from a nearby explosion rather than abstract theory. Planetariums will create shows featuring the event. Science museums will build exhibits. The supernova will become a cultural touchstone, referenced in classrooms for decades as the moment when theory met reality. The explosion will also drive technological development. Detector sensitivity will be pushed to new limits. Data processing algorithms will be refined to handle unprecedented volumes. New instruments will be proposed and funded based on lessons learned from Betelgeuse. The scientific infrastructure developed to study this single event will benefit astronomy broadly, improving our ability to observe and understand the universe long after the supernova fades. The ancient skywatchers who saw it coming, long before modern telescopes, before scientific instruments could measure stellar distances or predict explosions, humans watched Betelgeuse. Ancient civilizations noticed its distinctive red color, its variable brightness, and its prominent position marking Orion's shoulder. They wove it into myths, used it for navigation, and tracked its changes across generations. If Betelgeuse had exploded 2,000 years ago, ancient astronomers would have documented an event that modern science could still analyze. This raises a fascinating question. Did they already notice something we're only now discovering? Historical records preserve observations of bright, transient events. The oldest recorded supernova appeared in 185 CE, documented by Chinese astronomers as a guest star that remained visible for months. The 1006 supernova was so bright that shadows could be cast by its light, witnessed and recorded in China, Japan, Egypt, Iraq, and Europe. The 1054 supernova created the Crab Nebula, recorded extensively in Chinese and Japanese texts. These historical supernovae were distant thousands to tens of thousands of light years away, yet they made such an impression that records survived for centuries. Betelgeuse is 30 times closer than the 1054 supernova. If it had exploded while ancient civilizations flourished, it would have been the brightest object in the night sky after the moon, visible during daylight for weeks. Such an event would have been impossible to ignore, generating records in every literate culture on Earth. The absence of such records in historical astronomy is itself evidence Betelgeuse has not exploded during recorded history. But the ancients noticed other things about this star that suggest they were tracking changes we're only now measuring precisely. Ancient Egyptian astronomy provides intriguing hints. Egyptian calendars were tied to the heliacal rising of Sirius, the date when the star first became visible just before sunrise after a period of invisibility. This event marked the beginning of the Nile's annual flood. But Egyptian texts also reference other stars, including those in the Orion constellation, which held religious significance as the celestial representation of Osiris. Betelgeuse, as part of Orion, would have been observed regularly. Some Egyptologists have noted references to a red star in Orion that may correspond to Betelgeuse, though interpretations remain debated. Greek astronomy offers more concrete evidence. Ptolemy's star catalogue, compiled around 150 CE, describes Betelgeuse as reddish. But interestingly, earlier Greek texts, including works by Hipparchus around 150 BCE, contain descriptions that some scholars interpret as describing Betelgeuse differently. This has led to speculation about whether Betelgeuse's colour or brightness changed noticeably between the time of Hipparchus and Ptolemy to a span of 3 centuries. If true, it would indicate long-term variability beyond the short-period changes we observe today. Chinese astronomical records are particularly valuable because they span millennia and were maintained continuously by imperial astronomers whose job was to track celestial changes. Chinese star catalogues describe Betelgeuse's position and note its colour always as red or reddish-yellow. But some records contain references to brightness variations that might correlate with the kind of dimming event observed in 2019 to 2020, when Betelgeuse lost more than 60% of its brightness. If ancient Chinese astronomers noticed similar dimmings, their records could extend our baseline for understanding Betelgeuse's behaviour across much longer timescales than modern observations provide. Arab astronomers of the medieval Islamic Golden Age made precise measurements of stellar positions and brightness. The name Betelgeuse itself comes from Arabic, likely derived from Yad al-Jawza, meaning hand of the giant, referring to its position in Orion. Arab star catalogues describe its colour and position, and some contain notes about variability. These observations, if fully analysed and cross-referenced with modern data, might reveal whether Betelgeuse's variability has changed over the past millennium. Indigenous astronomical traditions also observed Betelgeuse. Australian Aboriginal astronomy, with oral traditions spanning tens of thousands of years, includes stories about Orion and its stars. Some Aboriginal groups tell stories of a red giant or hunter whose fate involves transformation or death narratives that could preserve ancient knowledge of stellar changes. While interpreting these stories requires caution to avoid overinterpretation, they demonstrate that pre-scientific cultures noticed and remembered stellar characteristics across many generations. Native American astronomy similarly includes Orion in various myths and seasonal markers. Some tribes used Betelgeuse's position to track agricultural seasons. The star's visibility in evening or morning skies correlated with planting or harvest times. If Betelgeuse's brightness had changed dramatically in pre-Columbian times, it might have affected these calendrical systems, potentially leaving traces in oral histories or ceremonial practices. The challenge with ancient observations is distinguishing real astronomical events from mythological embellishment. Did a particular culture's story about a dying or transforming star reflect actual observation of brightness changes, or was it pure mythology? Modern archaeoastronomy attempts to answer these questions by correlating ancient records with known astronomical events. But many questions remain unresolved. One intriguing possibility: if Betelgeuse has been dimming slowly over millennia, ancient observers might have recorded it as brighter than we see today. Some stellar evolution models suggest that red supergiants undergo long-term variability over thousands of years as they exhaust different fuel sources in their cores. If Betelgeuse was notably brighter 2,000 years ago, ancient brightness estimates might differ systematically from modern measurements. Comparing ancient descriptions with current brightness could test these long-term evolution models. The historical record also preserves something else valuable: continuity. Because Betelgeuse has been observed for thousands of years without exploding, we know its pre-supernova lifetime is at least that long. Combined with stellar evolution models, this constrains how far along it is in its final stages. A star that explodes within years of first observation is different from one that has been observed for millennia. Betelgeuse falls into the latter category, suggesting that while it's in its final phase, the timescale is uncertain enough that we cannot predict the explosion more precisely than sometime in the next 100,000 years. If Betelgeuse explodes during our lifetimes, we'll create records that future civilizations will study: high-resolution images, spectra, light curves, neutrino data, a comprehensive archive preserving every detail. These records will serve the same function for future astronomers that ancient Chinese supernova records serve for us. They'll provide data points for understanding stellar evolution on timescales longer than individual human lifetimes. The explosion will be documented so thoroughly that scholars 10,000 years hence, if they exist, will still be analysing it, extracting information we don't yet know how to look for. The Betelgeuse evacuation that will never happen. In science fiction, when a star threatens to explode, civilizations evacuate. Fleets of starships carry billions to safety. Entire planets are abandoned. It's dramatic, compelling, and utterly unnecessary for Earth. Betelgeuse's explosion poses no evacuation-level threat. But exploring the hypothetical "what if it did?" reveals just how unprepared humanity is for existential cosmic threats and what a real evacuation scenario would require. Start with the timeline. If Betelgeuse's core collapsed tonight, we wouldn't know for 642 years the time light takes to travel from there to here. When we finally detect it via neutrino burst and then optical brightening, the explosion has already happened. There's no warning period where we detect pre-supernova indicators and evacuate. By the time we know, the event is over. This fundamental limitation that we see cosmic events only after they occur eliminates most evacuation strategies that might work for predictable disasters like hurricanes or volcanic eruptions. But suppose, hypothetically, advanced detection methods gave us warning. Suppose instruments somehow detected core collapse signatures in real time before light arrived. Even with decades of warning, evacuating Earth's population is impossible with current technology. Earth has roughly 8 billion people. Our most advanced rockets can carry perhaps 10 people to space at a time. Even launching continuously, evacuating everyone would take millions of flights. The logistics are staggering. Fuel, manufacturing, launch facilities, spaceports, training. We lack the industrial capacity to build millions of spacecraft, let alone do so within decades. Where would people go? The Moon? Mars? Both are less habitable than the most extreme environments on Earth. Even if Betelgeuse's radiation was catastrophic, which it isn't, surviving in underground bunkers on Earth would be easier than establishing self-sustaining colonies on airless worlds. Space stations? The ISS supports 6 people. Scaling that to billions requires infrastructure that doesn't exist and can't be built quickly. Generation ships to other stars? The nearest potentially habitable systems are light years away. Travel time would be centuries at minimum. We'd need closed-loop life support, artificial gravity, and reliable propulsion technologies that remain largely theoretical. Cost presents another barrier. Launching 1 kilogram to low Earth orbit costs roughly $2,000 to $5,000 depending on the rocket. Launching a 70-kilogram person with minimal supplies costs $140,000 to $350,000. Evacuating 8 billion people would cost $1.12 to $2.8. Quadrillion, more than 10 times global GDP. The economic resources don't exist. Even if governments diverted all spending to evacuation, they couldn't generate the necessary wealth fast enough. Energy requirements are equally prohibitive. Rockets burn enormous quantities of fuel. A Falcon 9 launch consumes about 400,000 kilograms of kerosene and liquid oxygen. Launching millions of spacecraft would require fuel production exceeding current global capacity by orders of magnitude. Refining, transporting, and storing that fuel would strain energy infrastructure to the breaking point. Renewable energy couldn't scale fast enough. Fossil fuels would be exhausted. Nuclear energy might help, but couldn't fill the gap entirely. Political challenges compound technical ones. Who gets evacuated first? Wealthy nations would dominate early launches, creating inequity. Poorer nations would be left behind, sparking international conflict. Within nations, who decides priority? Young and healthy? Skilled workers? Political leaders? Lottery systems? Every choice creates ethical dilemmas with no satisfactory resolution. Historical precedent from disasters shows that evacuation prioritizes elites, leaving vulnerable populations behind. A global evacuation would exacerbate these inequalities dramatically. Social cohesion would collapse under evacuation pressure. Knowing that billions would be left behind, while a few escaped, would trigger unrest, riots, and violence. Governments would impose martial law to maintain order. Borders would close. Hoarding would be rampant. The fabric of civilization, cooperation, rule of law, mutual aid would fray rapidly. The evacuation itself might cause more deaths through societal breakdown than the cosmic threat ever would. Contrast this with what's actually required for Betelgeuse. Nothing. The radiation is manageable. The neutrino flux is harmless. The cosmic ray increase is detectable, but not dangerous. No evacuation is necessary. Preparedness involves monitoring atmospheric changes, adjusting satellite orbits, and perhaps temporarily increasing cancer screening measures incomparably simpler than evacuating Earth. This mismatch between science fiction's dramatic evacuations and the mundane reality reveals how distorted our cultural perception of cosmic threats has become. Yet the thought experiment is valuable. It exposes vulnerabilities. If a genuinely catastrophic cosmic event threatened Earth, a gamma ray burst from a closer star, a rogue black hole passing through the solar system, a massive asteroid impact, we lack the capability to respond effectively. Our space infrastructure is embryonic. Our interplanetary colonization is non-existent. Humanity is confined to Earth with no backup. This realization should motivate space development not as a response to Betelgeuse specifically, but as insurance against genuinely existential risks. Establishing self-sustaining colonies on the Moon and Mars, developing advanced propulsion systems, building orbital habitats, these projects serve long-term survival. Not because Betelgeuse threatens us, but because a single planet species is vulnerable. Betelgeuse's explosion while not dangerous, can serve as a catalyst for recognizing that vulnerability. The paradox is that the one cosmic event guaranteed to happen, the Sun's eventual death in 5 billion years, is so distant that it motivates no action. Betelgeuse, which could happen any time but poses minimal threat, generates attention precisely because it's unpredictable and spectacular. This suggests that human psychology responds to immediacy and drama rather than long-term, abstract risks. Effective policy must account for this bias, framing space development not as defense against specific threats, but as prudent, long-term planning. If we ever do develop evacuation capability, it won't be for Betelgeuse. It will be for threats we haven't identified yet, or for proactive expansion driven by curiosity and ambition. The infrastructure built for exploration, reusable rockets, orbital construction, closed-loop life support would coincidentally provide evacuation options if needed. But evacuation would be a side benefit, not the primary goal. For now, Betelgeuse requires no evacuation. It requires observation, preparation for minor disruptions, and public education to prevent panic. The explosion will be a spectacular, scientifically invaluable event that poses minimal danger. The real lesson isn't that we need to evacuate Earth. It's that we need to expand beyond Earth, not from fear, but from wisdom, recognizing that a single planet is a fragile home for an ambitious species with a long future ahead.